So chapter 8 is all about alkenes and elimination reactions. I told you guys already that chapter 8's really similar to chapter 7, but with some new twists. So some people find this to be the hardest chapter in first term organic. I hate to say it. The first thing that I already did for you guys was I created a supplemental video on alkene nomenclature. That video is on the website, or you can use the hyperlink that's on the pod and watch it tonight in order to complete the alkene naming section. The naming's really, really easy. However, there are some new rules that we kind of throw in. Primarily, we have to assign stereochemistry to alkenes using E or Z nomenclature. So make sure that you understand that. You can also read through the book or come ask me questions if that video still doesn't make sense. But let's continue on to alkene stability really quick. Not all alkenes are created equal. Some alkenes are more equal than others, just like some carbocations are more equal than others, right? So if we think about carbocation stability, what made a tertiary carbocation more stable than a secondary? What was that effect? Does anybody remember? Not quite induction. It started with an H. Hyperconjugation, right? So hyperconjugation stabilizes carbocations. Hyperconjugation also will stabilize alkenes. So if we look at an alkene, we could say, all right, this could be a simple alkene. We would call this monosubstituted. Meaning it's got one carbon substituent coming off and 3 hydrogens. If we continue and we look at a disubstituted alkene, there's 2 different types. We could have this alkene or this alkene. What's the difference between those? Cis or trans. We've got the cis one on top, the trans one on the bottom. They're both disubstituted, right? So we could call these disubstituted. Additionally, we can go on and we can say there's also tri-substituted alkenes, and then there are tetra-substituted alkenes. Which one do you think is going to be most stable, the tetra-substituted or the mono-substituted? Tetra. So again, just using that simple hyperconjugation rule, we know that we get more stable due to hyperconjugation. Pretty straightforward. There's also another caveat with alkene stability, and that's specifically when we compare cis and trans isomers. So let's take a look at what I mean by that. So cis versus trans. Let's think about which one would be more stable, this trans isomer or the cis isomer. Which one do you think is more stable? Trans? Does anybody want to throw out their hypothesis as to why trans is more stable?
Bonds, or it doesn't have as much bonds.
What do you think, Athea?
The substituents are going to be interacting with each other.
Yeah, they're not going to be interacting with one another, right? If we think about the hydrogens coming off here, let's even draw them in, just for good measure. We can see the hydrogens on this cis substituent actually are kind of running into one another in almost like a gauche or eclipsed interaction. So that's destabilizing, versus over here, these methyl groups are much, much further away, so we don't have that steric clash. So typically, your cis isomers will be significantly less stable than your trans isomers. So we'll say less stable due to sterics. Which is a little bit weird to think about, because if you think about fats in your body, right? Our body only makes cis fats. We don't make trans fats naturally. So essentially we're forcing fat production into the less stable isomer. It's a little weird to think about, but it's how our bodies have evolved. All right, so let's talk a little bit about how we can prepare alkenes. Alkene preparation we've already seen in lab with our cyclohexene lab, but there's actually 2 different ways to prepare alkenes. we'll talk about method number 1 first. And then we'll compare it to a second method. So in the first method, we have this leaving group on here. I'll just label it LG. And we're going to react this with some sort of base, and I'll call this base B minus. First thing you do when you're looking at these sorts of reactions is you identify the carbons as either alpha or beta carbons. Your alpha carbon is going to be the carbon that's directly attached to your leaving group, and your beta carbon is going to be one carbon further away. So alpha equals the position with the leaving group attached. What would we call it if it were one further away? Alpha, beta, what goes after beta? Gamma. We'll talk about gamma protons later on in the year. But in this chapter, we're primarily concerned with beta positions. Beta positions are where the action happens. Specifically, we need to identify protons on the beta position. So we've got beta protons right here in blue. Or we could also identify beta protons over here. Does it really matter which one we pick? Not really, they're equivalent. So in this case, what's going to happen is your base is going to go and grab a beta proton. Actually, let me change this. There we go. So we're going to grab this beta proton. And if we're going to steal that proton, this covalent bond has to go somewhere. So we're going to clamp that down between the alpha and beta position, form a new pi bond. And then last but not least, we're going to kick off this leaving group, all in one step. It's almost like dominoes. So you're grabbing that top beta proton, it falls down, forms a pi bond, and then kicks off that leaving group. So if we do this, we've now got an alkene where we've got these remaining beta protons. And let me actually draw in, or let's just erase these for now for clarity's sake. They're still there, but they're going to be unreactive at this point because you don't have any more leaving groups. And then our conjugate acid in this case is going to be HB, and it's now going to have, a neutral charge. All right, so what do you guys think the rate order will be for this? You think it'll be first order, second order, third order? Let's think about this. Does it rely on a collision between two molecules, or does it rely on one molecule spontaneously doing something? A collision between two molecules, right? Your base is grabbing something off of your starting material, so you're relying on the interaction between two reagents. That means it's got to be second order, right? So let's make a note of that. It relies on the collision or reaction between two reagents. That means that our rate in this case is going to be equal to our little k times our substrate, which is basically our starting material, times our base concentration. So this looks pretty similar to a reaction that we saw previously where we had the nucleophile slamming into our electrophile, kicking off a leaving group all in one concerted step, right? So in this case, this is called an E2 reaction rather than an SN2 reaction. And the E stands for elimination instead of substitution. And the 2 stands for second order. So that's one main type of elimination reaction. These are pretty common anytime you've got a really strong base and you've got beta protons that are available next to a leaving group. The second type is going to be analogous to our SN1 reaction. So let's take a look at method 2. If it's like an SN1 reaction, what do you think the first step's going to be? Yeah, leaving group falls off. And we know in order for this to happen, we have to be able to form some sort of relatively stable carbocation. So let's make a note of that. You must have a good leaving group. And you must form relatively stable carbocation. It's the same requirements as with an SN1 reaction. All right, so after this, we've got our leaving group floating around. And where do you think the alpha position is going to be now? Where's the electrophile? Yeah, where the positive charge is. So just like in the previous example, alpha is where your electrophile is at. Beta is going to be 1 carbon away. So we've got actually 3 different beta carbons here. And in this sort of reaction, we need to identify protons coming off a beta carbon just like we did before. And if we have a base around, this base can reach over, grab one of those beta protons, clamp down, and we can form our alkene, our conjugate acid, and in this case we also have our leaving group falling out or floating around in solution.
Would the conjugate acid be positive? Or?
Yeah, in this case our base was neutral, which means our conjugate acid would be positive. Oftentimes, just like with an SN1 reaction, you don't need a really strong nucleophile. With an E1 reaction, where it's first order, you oftentimes don't need a strong base in order for it to occur. They're really similar in that regard. So in this case, what's the rate going to be? The rate equation, I should say. Yeah. The rate's just going to be dependent on the concentration of your substrate or your starting material. It's not impacted at all by the concentration of your base. So just like with our E2 analogy, we would call this E1 because, again, this is going to be an elimination reaction. And this will be first order. If we think about the reaction that we did in lab, was that an E1 or an E2 reaction? Let's go back and look at what we did in lab. So review from lab. In lab, we said we started with cyclohexanol. And we had some sort of catalytic acid. I'll throw that in brackets here. And in the first step, we protonated our alcohol, right? In fact, let me do equilibrium arrows for this one. And now we've got a really good leaving group on our molecule. That means after this step, we're going to kick off this water. And we're going through a carbocation intermediate. That immediately indicates that it's an E1 reaction. Similar to an SN1 reaction, an SN1 reaction always has a carbocation intermediate. Same is true with E1. And in this case, we need to identify our alpha and beta positions. Our alpha, we said, is always going to be that electrophile. So it's either the carbon with the leaving group attached or the carbon containing the positive charge. And then we've got beta over here. And we've got beta over here. Let me actually move this beta down a little bit. And we know the beta positions. It doesn't matter which side we pick from. We've got 2 of them. And just like we saw in lab, this weak base can come grab this proton, clamp down, and we were able to form cyclohexene in lab plus our hydronium. So E1 reactions, like I said, are really, really similar to SN1 reactions. There's a ton of different variables we've got to consider when we're comparing the two. However, we're going to be spending the rest of the week really looking at all of those ins and outs. Are there questions? Yep.
Why is it an equilibrium error between the carbocation being rearranged, or not being rearranged, but being turned into an alkene and the final step? Because aren't carbocations unstable?
Yeah, so you're saying why do we have an equilibrium arrow for this last step?
Yeah.
Oh man, you're getting into some interesting chemistry there. So if we think about this, we said in lab this reaction, if we had acid in there and water, could actually go in the reverse direction. And I think I brought it up in all the lab sections. We said delta G equals delta H plus negative T delta S. And in this reaction, are we increasing disorder or decreasing disorder? Increasing disorder, right? So for this reaction, or for really any elimination reactions, you're going to be increasing disorder. So delta S is going to be positive. So if we think about this, that means that this whole sign is going to be negative for elimination reactions. So does it really matter what delta H is if we crank the temperature up high enough? Not really. However, if it's cold, that delta H becomes really important, right? So that equilibrium arrow is really dependent on temperature. For elimination reactions at high temperature, you're definitely going to favor that alkene formation, but under low temperatures, you might actually go in that reverse direction. So for elimination reactions, delta G becomes more negative, meaning it's spontaneous, at high temps. If you were to run this reaction at a low temperature, you might actually favor that starting material side and not your product side. And that's the first reaction we're going to start off with when we come back from winter break. Those are called addition reactions rather than elimination reactions.
That note there, that's for the entire elimination reaction, not just the last step that you're referring to.
Yeah, for pretty much every single elimination reaction that we'll see, we're going to be increasing disorder because you're kicking off a leaving group and forming an alkene.
But the carbocation and alkene, they're not talking about those two steps because there's two moles each on both sides.
Yeah, what we're really looking at is comparing
Just that one going
our starting material. Up here we've got 1 mole, and down here we've got 2 moles. So we're looking at the net spontaneity from our starting materials to our products. Make sense? All right, tomorrow when we come in, we're going to talk a lot more about the mechanistic details behind E2 in particular.